Hello and welcome to this partner webinar together with Laird Connectivity. Today we will be talking about the BL5340PA module by Laird Connectivity. It does include both the nRF5340 SoC and the nRF21540 RF front-end module for extended range. I'm one of your hosts today. My name is Björn Kvåle. I'm a product marketing engineer at Nordic Semiconductor, and with me I have Jonathan Kay, who is the VP of Product Management and Marketing at Laird Connectivity. Just some quick practicalities before we get started. So the duration will be approximately 50 to 60 minutes with a roughly 45-minute presentation and a 15-minute Q&A. The questions are encouraged, but please type the questions at the top of the right sidebar. All of these questions are anonymous, but try to keep them relevant to the topic. We will answer questions towards the end in the Q&A slot. The chat on the bottom right, which you can see here, is not anonymous and should not be used for questions. If you do have more questions after the webinar is done, feel free to go to DevZone for Nordic Semi-related questions. So that's devzone.nordicsemi.com, or you can go to lairdconnect.com/contact for Laird Connectivity related questions. And last but not least, a recording of the webinar together with the presentation will be available at webinars.nordicsemi.com shortly. So, quick agenda before we get started. First, I'll give an overview of the Nordic nRF5340 Advanced Dual Core Wireless SoC and the nRF21540 RF front-end modules. I will go through in a bit more details on the architecture description of both the nRF5340 SoC and the nRF21540. And then Jonathan will go through an overview of how they are integrated into a certified BL5340PA module range from Laird Connectivity. And then we'll also review some use cases, or he'll review some use cases where this solution maximizes product performance and wireless range. Okay, so without further ado, I'll start with an overview of the nRF5340 and the nRF21540. Let's get started with the nRF5340 overview and highlights. So on the figure on the left, you can see the nRF5340 SoC. So it includes both an application processor and a network processor. On the application processor, we do have a 128 megahertz ARM Cortex-M33 with 1024 kilobytes of flash and 512 kilobytes of RAM. On the network processor, we do have 64 megahertz ARM Cortex-M33 with 256 kilobytes of flash and 64 kilobytes of RAM, in addition to a redesigned Multiprotocol 2.4 gigahertz radio. So we've essentially optimized the application processor for high performance, and we have a very efficient network processor, which is fully programmable. So a lot of our competitors do not have a fully programmable network processor, whereas this is the case with us. So that does provide, software flexibility. We do also support advanced security features such as cryptocell, secure storage, and also runtime isolation via ARM Trust Zone, in addition to other security features. On the supply range, it is 1.7 to 5.5 volts. So that is very good for both battery operation, but also for USB power. And the operating temperature range is extended from minus 40 to plus 105 degrees Celsius, which is very useful for things such as professional lighting. So applications such as professional lighting. I'm going to talk quickly about multi-core flexibility. So we have optimized the application processor for high performance, and we've optimized the network processor for high efficiency. So there is no trade-off. We can basically optimize both for performance and efficiency. And this is very hard to do if you only have one processor. So by having two processors, you are able to optimize for both performance and efficiency. We also do have separation of concerns. So real-time requirements, there are often real-time requirements in embedded systems and especially in wireless protocols, which makes it difficult sometimes to satisfy those real-time requirements while also doing other stuff in your application. In this case, by basically having the wireless protocol stack on the network core, this does free up your application to do other things that it should be doing. So that is a major benefit. We also do have software split, so you can leave the thoroughly tested wireless protocol stack in the network core while you develop your application in the application core. Let's move on to the multi-protocol radio. So the multi-protocol radio does support Bluetooth version 5.3 and beyond. So this includes LE audio, direction finding, also Bluetooth 5.0 features such as 2 Mbps, long range, and advertising extensions. We also do have support for Bluetooth mesh and 802.15.4 based protocols such as Thread and Zigbee. We also do have support for Matter. This is not exactly a protocol. It's mainly something sitting on top of the protocol, but I just wanted to mention that we do have support for that on the nRF5340. Let's move on to radio improvements. So the TX current has been reduced by 29% down to 3.2 milliamps. This is compared to the nRF52840 SoC, seeing that that was our last flagship SoC. The RX current has been reduced by 41% down to 2.6 milliamps. This is very useful for applications that need to listen a lot. So for example, LE audio and Bluetooth mesh, there you are listening a lot for incoming packets. So very useful to have a decreased RX currents. The radio RX sensitivity has been improved by 3 dB from the nRF52840 to minus 98 dBm. And so essentially what you are getting is a 3 dB improvement in RX sensitivity while also reducing the RX current by 41%. And last but not least, we also do have a 1 dB resolution of TX power. So on the nRF52840, this was 4 dB, whereas now it is has been decreased down to 1 dB. All in all, the nRF5340 is an nRF52 series feature superset. So it does have support for Bluetooth 5.3, Thread and Zigbee, CryptoCell, which is essentially hardware accelerated cryptography, USB, QSPI, and also high-speed SPI, the operating temperature of 1.7 to 5.5 volts, and also the extended operating temperature. So in essence, what you're getting is more performance, memory, and integration, while also minimizing the power consumption. Okay, let's move on quickly to the nRF21540. This is our RF front-end module. It does include both a power amplifier to essentially increase the TX output power, and it does include a low noise amplifier to get better RX sensitivity. It does support Bluetooth LE and Bluetooth mesh, so everything that I already mentioned before for the nRF5340. It does support Thread and Zigbee and also 2.4 gigahertz proprietary. We do have plus 13 dB receive gain with a 2.7 dB noise figure, which does give up to 5 dB improvement in the RX sensitivity versus just using an nRF52 or nRF53 series SoC. And it does also provide configurable TX output power up to 21 dBm. So we do also provide a control loop, and That is to get accurate and legal output power. So whereas before, if you do have a variation with a 52 series of plus minus 4 dB, customers that, for example, needed 20 dBm would need to set an output power 4 dB lower. So with this control loop, you are basically able to set the output power a lot more granularly than before. Okay, so depending on which SoC you use, plus the nRF21540, it is configurable to be Arab, ETSI, and or FCC approved. On this link, there's a link to a table which shows some of the TX output power values. That varies depending on the region, but also a bit depending on which protocol you are using. For the interfaces and the TX gain control, we have GPIO control, SPI control, or a combination. SPI control allows you to more granularly set the TX gain. In addition, there is also antenna switching support and also power modes. We do have a single-ended 50 ohm matched input and output. There is also antenna diversity support, so for applications such as Thread and Zigbee to combat multipath fading effects. There is no bypass mode support, so that means you do always need to use the nRF21540. You can't bypass the 21540. On the operating condition side, there is a 1.7 to 3.6 volt supply range, and also the same extended operating temperature of minus 40 degrees Celsius to plus 105 degrees Celsius. Great for things such as professional lighting. And last but not least, package variants is a 4x4mm QFN16 with a 0.65 millimeter pitch. Now I'll move on to a detailed architecture description for both the nRF5340 SoC and the nRF21540 RF front-end module. So here we can see a block diagram of the nRF5340 SoC. You can see both power and clock, application processor, in addition to the network processor. I'll talk a bit more about each in a later slide. Communication between the application processor and the network processor is done via IPC, so the IPC inter-processor communication, and also the advanced security features. They are located on the application processor, while peripherals for doing AES on the wireless protocol is on the network processor. Also advanced peripherals like we have USB, quad SPI, high-speed SPI is on the application core. Okay, let's talk a bit more about the application processor. It does have an ARM Cortex M33 with DSP and floating point instructions. It has 128 megahertz and 64 megahertz clock speeds, where 128 megahertz is optimized more for performance, while the 64 megahertz is optimized more for efficiency. But I have a later slide that goes into more details there. We do also have voltage frequency scaling, where depending on which clock speed is chosen, the internal voltage will change, which then optimizes for power efficiency. We also do have ARM trust zone support, in addition to an 8 kilobyte two-way set associative cache. And here on the application processor, we have 1024 kilobytes of flash and 512 kilobytes of RAM. Moving on to the network processor, here we also do have an ARM Cortex M33 with a 64 megahertz clock speed. This one is optimized for efficiency. It is also fully programmable, so that does give software flexibility. You can decide yourself what you want to put on the network processor. And this is not the case with a lot of our competitors. We also do have 2 kilobytes of instruction cache here, in addition to 256 kilobytes of flash and 64 kilobytes of RAM. And like I mentioned before, the IPC is the block that is used to then communicate from the application processor to the network processor. And we also do have the multi-protocol radio on the network processor. Let's move on a bit to multi-core flexibility. So here we can see on the x-axis, we can see efficiency in core marks per milliamp, and on the y-axis, we can see performance measured in core marks. This is all compared to the nRF52840 because that was our latest flagship SoC. We can see if we're running the app at application core at 64 megahertz, we can actually see we get better performance in addition to better efficiency. And when we run the app at 128 megahertz, we can see way better performance, so more than 2 times better performance compared to the nRF52840, while also being more efficient in addition. And also to note is that the frequency of the application core can be changed at runtime. So normally you'd run at 64 megahertz, but if you have a task that does require more performance, you can then switch to 128 megahertz, and then you can switch back down to 64 megahertz once you're done with that task. And on the network core, running at 64 megahertz, you can see the performance is actually, it's better than the nRF52840, and it has a lot better efficiency. So 101 core marks per milliamp compared to 64 core marks per milliamp. Moving on to the power and clock. So like I said previously, we have a 1.7 to 5.5 volt supply that can either be done via LDO and DC-DC, where DC-DC is the more power efficient option. You also do have direct supply from USB. On the oscillator side, you do have integrated load capacitors in addition to a 32 megahertz and also optional 32 kilohertz crystals. One thing to note is we also do have a tunable on-chip audio PLL, so that can either be at 11.289 or 12.288 megahertz, and there's a very low jitter, which is very suitable for audio applications. Good to note, we also do have an nRF5340 audio development kit if you do want to get started with audio applications. Let's move on quickly to the nRF21540. There you do have up to 10 times range increase. This is of course dependent on which SoC you use the 21540 with. In this case, we are comparing to the nRF52840, just as an example. So if we only use the nRF52840 on both sides in a symmetric link, we get a TX of 8 dBm on both sides and an arc sensitivity of minus 95 dBm. If we add an nRF21540 to both sides and we're able to run at TX 20 dBm, this depends a bit on which region you are in. But assuming you can do that, you can see the TX gain improves with 12 dB. So you get a 12 dB improvement on the TX side and a 5 dB improvement on the RX side. So in total, that is a 17 dB improvement. And if we take the, if we say that 6 dB roughly doubles the range, then 17 dB is roughly an 8 times theoretical range improvement. But of course, this depends quite a lot on the conditions, so you need to, of course, test this yourself. This is just a theoretical value. So we can see between a 6.3 and 10 times range in a symmetric link. And this does depend which of the nRF52 series you do use. For the nRF5340, if we do the similar calculation to this figure here, you get roughly a 9 times theoretical range improvement. On the RX side, it is up to 5 dB improvement in RX sensitivity if you use an nRF21540. And this is very useful for protocols such as Bluetooth Low Energy, Bluetooth Mesh, Thread and Zigbee, and also 2.4 gigahertz proprietary applications. One of the other benefits of using an nRF21540 is the increased link robustness. So you do get up to 20 dB increased link budget. Like I said, up to 17 dB from the TX and up to 5 dB from the RX, dependent on which wireless SoC you are using. You also do minimize the packet loss and retransmissions. So depending on your use case, the less packet loss can benefit current consumption. It also does lead to improved communication latency. And one cool thing to note is you do have the option of doing dynamic output power adjustments. So customers are able to optimize the link budget via RSSI measurements to improve link robustness when the link environment or the link range changes. So by this we mean if you are getting good RSSI measurements, you can of course lower the TX gain to save power consumption. But if you notice that the RSSI measurements, if the link robustness is not good enough, you can always increase the TX gain a bit to get better link robustness. And one thing to note too is we do on the Bluetooth LE, we do have a Bluetooth LE power control experimental support as of nRF Connect SDK version 2.2.0. You can find more information in our documentation. We also do have adjustable output power on the nRF21540. So this is adjustable to plus minus 1 dB around the 10 to 20 dBm TX output power. So this is both the ETSI and the FCC limits, and the upper limit is 21 dBm. We do have user programmable modes for TX gain and also worldwide coverage with one device with different output power settings are possible. So you can do these TX gain adjustments via SPI, GPIOs, or a combination of both. Okay, so that was it for me. I'll now hand it over to Jonathan from Laird Connectivity. He'll give an overview of how the nRF5340 and the nRF21540 are integrated into a certified BL5340PA module range from Laird Connectivity.
Thanks, Bjorn. I'll pick up now and relate the nRF5340 SoC and nRF21540 FEM into Laird Connectivity's BL5340PA module series. I thought I'd start with a high-level overview of the final product family, then break that down into how we achieved this, specifically looking at the hardware, software, and certification steps. The family consists of two hardware variants with integrated or external antenna options, both supported by a comprehensive development kit, which we'll circle back to later on. The modules expose all of the attributes of the two Nordic key components that Bjorn has outlined so far. They have regulatory certifications for the US, Canada, Australia, and New Zealand, with Bluetooth SIG controller subsystem approvals too. As you can see, we have chosen to optimize our design for the best mix of power consumption and output power. The nRF5340 SoC has plus 3 dBm of TX power, but our PA designs are certified for up to plus 18.5 dBm for BLE and up to 21 dBm for 802.15.4. Layered over all of this are Laird Connectivity's core value-added pillars of software, support, antennas, certification, and a decade of Nordic module designs that ensures we get you to the market faster with the least possible design risk. Okay, so let's turn our attention to the how, starting with the module hardware. I figured this slide would be a good visual representation of the hardware design itself. On the right-hand side is our mass production module family, the BL5340 series, that incorporates only the Nordic nRF5340 SoC. On the left-hand side is the equivalent image for the new BL5340PA, adding in the nRF21540 FEM. We were able to keep the width of the module the same, but had to extend the footprint lengthways to accommodate about 6 millimeters for the FEM. Now, if you start digging into this and do really a side-by-side comparison, This slide shows the top view of the module pinout with pin definitions. The first thing to note is the pin count at 97 pins. It's a lot of I/O and capabilities to bring to the edge of the module to support the variety of potential customer implementations, and is a cause of the module growth over the original BL5340. Additionally, we've included more ground pads to ensure we ground the nRF21540 both electrically and thermally in our design. You'll see these in red highlight. Secondly, the BL5340PA has 8 less GPIOs, as these are needed internally for the nRF21540 FEM control, and we'll walk through those specific interconnects on the next slide. In blue highlight, you'll see how the 8 pins are marked as NC, no connect, versus the BL5340 design. Finally, outside of a single pin, number 72 marked here as no connect. All other GPIO are in the same place as the original BL5340 module. Pin 72 is due to there being no RF tracepad variant of the BL5340PA compared to the original BL5340 module. On this next slide, what you're looking at here is the interconnect layout between the nRF21540 and the nRF5340 module, nRF5340 inside our module. The BL5340PA design has been carefully optimized for the best RF and power consumption, both active and sleep performance. The key points to note here: the FEM uses GPIO pin control from the nRF5340. Our design has the FEM default TX gain fixed to 20 dB. This is the mode pin low setting. This TX gain is already calibrated by Nordic on a per chip level to be 20 dB plus or minus 0.5 of a dB. The module's RF TX power is varied by changing SoC TX power setting, and we've maximized TX power per channel and per PHY using this. From an active current perspective, the FEM's active peak current dominates that of the SoC, so is the key current driver in this design. Meaning when the FEM is powered down in sleep, the current is as low as 45 nanoamps, allowing our PA design to achieve the same sleep current as the non-PA based BL5340 module. One other aspect of our design to comment on is the voltage modes. We've deliberately designed the module series to support 3 to 3.6 volts, which is Nordic's normal voltage mode. You'll need to connect both the VDD and the VDD HV pins to your external power source, and this has been done as the RF TX power will drop with voltage. So at 1.8 volt, such as at 1.8 volt operation, and as noted before, we wanted to maximize this design for performance. A final note: if you want to use the USB interface on the module, you must externally fit a 4.7 cap to ground on the VBus pin, as shown in the middle bottom here in red text. All of this design optimization between the SoC and FEM ultimately enables a significant increase in link budget. Simply put, an idealized view on range maximization. This set of data is for the integrated antenna version of the PA module versus the original BL5340 below it. If you utilize the external antenna variants, you would see even greater range performance than this. The data speaks for itself. And just for full transparency, the LOS, the line of sight calculation represented here using free space path loss, is effectively equal to the link budget. As with all of the wireless products, range numbers are a guide only. You must test, and test again in your specific architecture and in your intended environments. Finally, on the last slide on the module architecture itself, a comment on the antenna choices for your specific design. For the layout image on the right-hand side, the nRF21540 has 2 antenna ports, ANT1 and ANT2, with control of them coming from the nRF5340 pin P0.04. Our module part numbers, the 453-00068 has an integrated PCB antenna and uses ANT1. The 453-00076 uses ANT2. But the key point here is that it has both the integrated PCB antenna and an MHF4 connector, enabling antenna selection or switching, if you require it, when the radio is not running. Finally, the 453-00076 variant is pre-certified with a wide variety of 2.4 GHz internal and external antennas, plus our NFC antenna to simplify your design and certification both in time and in costs. This last slide from an overall hardware standpoint is about the development kit, and I feel is a great visual of how Laird Connectivity looks to help our customers simplify enabling wireless connectivity in their designs. The DVK for each module variant is an extremely comprehensive set of reference designs for a large combination of peripherals and sensors that an IoT device maker will want to use in their final product. For example, it includes a TFT touchscreen display, Ethernet controller with RJ45 connector. It's got a Bosch BME 680 sensor, so a MEMS sensor for gas, humidity, pressure, and temperature, and air quality. It's got a 3-axis accelerometer from STMicro. There's an SD card there for storage. There's a connector to simply use the Nordic Power Profiler kit. Multiple power input options. USB to SWD, USB to UART from FTDI, all your usual array of LEDs, buttons, and easy to access headers. We've even included additional QSPI on there because your software team will say they need it just in case. And speaking of software, the next section here is 3 slides that are going to go through a high level of the software implementation we've done on the BL5340PA. This is what we've used for our own development and then certification of the module family. The Laird Connectivity embedded software team has generated specific board files for our complete BL5340PA development kits, which outline everything on both the DVK as well as the key characteristics of the module itself. One of the most critical aspects is the power table for these modules. All the logic that implements the power tables has been built into a Laird Connectivity driver and then pulled into nRF Connect SDK. The power tables document and control the specific radio channel settings to ensure that the regulatory certifications that we have per region are maintained without the user having to do anything. The only requirement on the customer is to build a project with our hardware boards file and pull in our driver. This ensures absolute confidence in regulatory compliance for the customer. All done for them, done and dusted. The Laird radio power tables have been designed to work with Nordic's MPSL, the Multiprotocol service layer, and to date is only currently available for customers developing within the framework of the nRF Connect SDK directly. Moving on to the certifications of the module. The module family is currently certified for FCC, so North America, ISED, Canada, and RCM, which covers Australia and New Zealand, for both Bluetooth Low Energy, as well as 802.15.4 for each of those regions. In addition to this, there are 6 internal and external antenna types pre-certified per region. There are power table loads for each of the regions to maximize the radio performance for the specific requirements of each region. A single universal power table could be produced, but that would lead to significant performance hits as it would bring down all of the settings to the lowest common denominator to get that single power table, so invalidating some of the optimizations in the different regions where power can be increased. A final note about CE UKCA. Currently, the BL5340PA family is not certified for CE or UKCA regulatory authorities. This is due to the complex requirements for how Bluetooth Low Energy radios can be declared with high output power under ETSI EN 300-328 version 2.2.2. The vast majority of Bluetooth Low Energy devices are declared as DTS mode, which has a requirement for power spectral density, PSD, testing which limits TX power to plus 10 dBm in Europe. The BL5340PA was designed specifically as a high-performance, high TX power device for extended range applications. This 10 dBm requirement and the additional software complexities offered offers really limited performance improvements over the globally certified standard BL5340 module that we showed earlier. Now that you've got your bearings on the BL5340PA module series itself, we'll start and now take a look at 4 different market applications and use cases where integrating the nRF5340 and nRF21540 into a single module provides significant benefits for those applications. The first of the 4 applications is for industrial manufacturing environments, for customers looking to utilize the modules as part of a predictive maintenance set of applications. Machine uptime is critical for optimal efficiencies of factory environments. The BL5340PA modules can be integrated with a variety of sensor ICs onto drives, valves, conveyors, motors, etc., and used to help monitor their behavior. The intensive artificial intelligence or machine learning software capabilities required can be run happily in the dual-core BL5340 SoC architecture and can help predict failure and maintenance needs before it even becomes a problem. The harsh operating environment, both in terms of the operating temperature and also from an RF perspective, make adding the FEM perfect to ensure that the maximum possible range between Bluetooth Low Energy nodes or to BLE gateway devices and then bridging the data to the cloud. If we then look at this from a second set of applications, the arrival of Bluetooth 5.2 as a specification brought with it LE audio with its isochronous channel support, and it brought promises of new use cases for audio applications using Bluetooth Low Energy radios. This slide looks to represent a future state LE audio implementation for public infrastructure needs in transportation. The concept being that using LE audio, you can broadcast unencrypted audio for public service messaging to phones and headphones. For example, such as in this use case, Platform 6, for the 359 to King's Cross, you can then add additional BLE guide location for digital pathways through that station. The module supports isochronous channels. The dual core enables efficient operation of the LC3 codec required for LE audio. And the FEM provides for the maximum range within these large, crowded facilities. The third use case I've got here is within asset tracking. Now this use case is for large distribution and warehouse facilities, needing location and asset tracking of a range of assets in this environment. That could be locating or finding physical goods, people, trucks, or the state of any sensors in the area, such as temperature or humidity control. The maximization of TX power and link budget enables coverage of such a large area with fewer devices and fewer gateways, so being overall much more cost effective. Additionally, the multi-wireless nature of the chipset from Bluetooth, 802.15.4, and NFC provides OEMs with maximum flexibility on the wireless architectures and use cases to serve that particular application need. Finally, our fourth market perspective is for medical in hospital or again larger scale medical facilities. The enhanced security capabilities of the nRF5340, such as ARM crypto cell, the root of trust, and secure key management, is ideally suited for applications in this market. The dual-core M33 architecture is perfect for black box separation of connectivity and application processing into separate cores. Aside from these benefits in optimized processing and security, supporting extended wireless range with the integrated FEM is ideal for these complex, congested RF spaces where locating and tracking of high-value medical electronics and equipment can be extremely challenging.
Thank you, Jonathan, for that great presentation. If you do want more information on the BL5340PA, feel free to head on over to lairdconnect.com/BL5340PA-series for more information. Okay, without further ado, let's head on over to the Q&A now.